This is going to be a overview and notes covering Le Chatelier's principle and the general idea of how changes to equilibrium are affected. So the general idea of equilibrium changes: if there's a change to the system at equilibrium, the reaction rates will adjust until a new equilibrium is reached. Now, the ratio of the products to reactants, that ratio will stay the same from the first equilibrium to the second equilibrium, but that does not mean that the concentrations are going to be the same as the first equilibrium, which we'll take a look at as we continue. But overall, the translation: if you mess with an equilibrium, then Q is no longer equal to K. And that means something's going to change to get the system back to equilibrium, or where the ratios of the products to the reactants equals the equilibrium constant. Now, many textbooks that are out there and even other websites will start talking about the idea that if a change is imposed on a system in equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. And that can be fairly confusing, so that's why I'm trying to reference this back to the idea of Q and the calculations that you can make. So the types of disturbances that you can have are in concentration, in temperature, and in pressure. Now, the changes of concentration and pressure, you will be shifting the equilibriums back to the same value for K. However, in temperature, the value of K actually changes. So the equilibrium constant is no longer constant, and we'll get into more details of that. So first, we're going to take a look at changes in concentration. So explanations for changing rates of reaction. If a concentration of a substance increases, then the rate is going to increase due to the greater likelihood of particles colliding. So the more type of that particle is there, the more likely they can collide, the more likely they're able to collide and react. You will have a shift, or you have an increase of the rate. If a concentration of a substance is decreased, the reaction rate slows due to particles less likely to collide. So ultimately, here is a data table that kind of summarizes overall the entire process when we're talking about concentrations changing and the disturbances to Q. Now, I do want you to note that when it comes to the Q being less than K, there are two different situations that can take place. You could either speed up a forward reaction, or you could slow down the reverse reaction. But either way, both of those events would cause a shift to the products. So you're producing more products more quickly in general if you are speeding up the forward reaction, or if you're slowing down the reverse reaction, you're just making the making of the reactants slower. Both of them have the same net effect, in which you're going to see an increase of products right away when you start to shift that equilibrium. Same thing is going to be true if you have the reverse of that. In other words, if Q is greater than K, again, you are going to get a shift to the left this time, or a shift to the reactants. And the explanations, as you can see, are either making products slower, or you are making reactants quicker. And in general, the rates of reaction, what are the two things that you can do? You can slow down the forward reaction, or you can speed up the reverse reaction, but the net effect of either of those is the same. The explanation may not be the same, but the net effect is the same. So, give you a moment to take a look at these particular questions. If the reactant concentration is increased, what happens to Q? If the reactant concentration is decreased, what happens to Q? What about products and being increased and decreased? And then last but not least, what about solids and liquids? I'll give you a moment to try that. So here are the resulting answers. I will leave this up for a moment as well to give you a chance to take a look at it. And then we're going to explore a little bit further into solids and liquids. So I'll give you a moment to look that over. All right. As far as solids and liquids are concerned, as long as you still have some solid remaining or some liquid remaining, there is no effect on the equilibrium position. Meaning, if you run out of solid, yeah, then there's going to be a problem. If you run out of the liquid, then there's going to be a problem. But as long as there's still some left in the container, Equilibrium can still be established, and the amount of solid or the amount of liquid does not really matter. So here are 3 examples that you can try based off of this equation that's listed. I'll give you a moment to answer those 3. So you'll notice if carbon monoxide is added, that means that Q will be greater than K. So if we add carbon monoxide, that means the products are now going to be at a larger number than the ratio should be. This means that Q is larger than K. Equilibrium will speed up the reverse reaction, creating more of the reactants. If carbon is added, there is no net effect because it is a solid. And as long as there was some solid there to begin with, adding more solid to it, not going to make a difference. If we were to remove arsenic out of this reaction, if we were to able to remove some of that arsenic out of the reaction, the Q would be smaller than K, which would mean that the reverse reaction is slowed down, and we actually are going to start producing more of the products to compensate and be able to get back to that equilibrium position. All right, so what you should be able to identify with each disturbance is the idea that, first of all, one, we just talked about Q. What happens to Q, or what happens to the value of K in terms of temperature, and we'll talk about that next. You should be able to identify what's happening with collisions, because once again, equilibrium is just a very fancy version of kinetics. What's going on with collisions that will increase or decrease the likelihood of those collisions to become fruitful in a chemical reaction. And then how those collisions affect the overall the reaction rates. Does it slow down the forward reaction or speed up the forward reaction? Does it slow down or speed up the reverse reaction? So you should be able to identify each of those under all of the circumstances that we look at. All right, as for temperature change. So when it comes to temperature changes, when the temperature changed, the equilibrium constant is changed. Okay, so when you change the temperature, you're no longer going to have the same equilibrium constant. The ratio of the products and the reactants will change, and this will change the value for the equilibrium constant. So if you take a look at this Maxwell-Boltzmann distribution curve with 4 different temperatures, what I want you to note is that if we were working with this first curve here of the 2M, you'll notice that there's just this small amount over here that would be able to form into either reactants or products, depending on whether or not we're looking at an exothermic or endothermic reaction. So we're looking at this small ratio to then this ratio of all of this stuff over here. However, that ratio will change very dramatically once you change temperature. So for example, if we then go to the red section, you'll notice the red section of this has a much greater amount of area covered in the portion beyond the activation energy. So this ratio to this ratio is now different, which means your value for K changes dramatically. Okay. So when you change temperature, one of the other things that you should be able to determine, assuming that you know that the reaction is exothermic or endothermic, is you should be able to determine what's going to happen to the value for K. Is the value of K going to increase compared to where you were before, or is it going to decrease compared to where you were before? So let's take a look at a few of those examples and explore the idea of exothermic and endothermic reactions as well. So as a review of endo and exothermic reactions, when the value for delta H is a positive number, so I want to point that out over here. When delta H is a positive value, this is an endothermic reaction, meaning that the reaction requires energy to be put into it. If you were to include that delta H into the balanced equation itself, you'll notice that it is written as a reactant because you have to put the energy into the reaction to make it happen, or at least to facilitate that reaction. So if the value for the delta H is a positive, put the energy on the reactant side of the equation. Energy is absorbed. All right, so then if we look at exothermic reactions, will have a negative delta H. So you'll notice we have a negative delta H down here. And when you have a negative delta H, please note that you then put the energies on the product side of the reaction instead of the reactant side. So these goes on the product side instead. Why is that? Energy is released. Or another way of describing that, energy is produced. You're releasing energy, and it is a product of the reaction. So if you have a negative delta H, it's on the product side. If you have a positive delta H or endothermic reaction, it's on the reactant side. And then at that point, you can generally treat the energy as if it were temperature and as a concentration. Like if you were to add energy to this, how would that shift the equilibrium? That would shift the equilibrium in that direction in a similar fashion that we talked about concentration. However, the explanation for why the equilibrium shifts is not so simple. So when there is a decrease in temperature, it's not going to be changing the value for Q. It will change the value for K. It's going to change the actual equilibrium constant. If you decrease the temperature in an endothermic reaction and you drop this down, you will make more of the reactants because the equilibrium will shift toward the reactant side. That now means your value for K, well, the value for the products is a smaller value. Your reactants is a larger value. So if that's the case, your value for K becomes smaller than it was before. So, and that's what we have denoted here. So a decrease in temperature on an endothermic reaction will cause more reactant to be produced, giving you a smaller K. And then you'll notice the opposite of that is true if you increase the temperature. By increasing the temperature, you make more product. The value for K would be larger. Okay. Now, do I recommend that you start memorizing this entire page of stuff? No, what I'd rather have you do is understand the idea that if you add temperature to this, that shifts the equilibrium this way. Products is now bigger than the reactants were before. Products are now bigger than they were before, and that now means your value for K is larger than it was before. So you should be able to do it through a series of logic rather than a set of memorization. Granted, if you're good at memorizing, go for it. I'm not going to stop you. Now you'll notice with exothermic reactions that if we are adding energy to the product side of this reaction, or actually we'd be adding energy to the entire reaction, but it would be affecting the reverse reaction. By adding energy, we would, by increasing the temperature, so we're doing this last one down here, by increasing the temperature, we would speed up the reverse reaction, making more making more reactants or less products. So that means the products would be smaller, reactants would be getting larger, and your value for K would become a smaller value than it was before. Okay. So let's take a look at this. You'll notice that there's a reaction at the top of the page. And hopefully you're able to identify the fact that this is an exothermic reaction because the energy is on the product side. Hopefully you can also recognize that the delta H of this reaction would be a negative value. So the reaction releases energy as a product, it's exothermic. If the reaction is heated, it will speed up the decomposition of the NH3. What will happen to the value of K when temperature is increased? Give you a moment to try that. So if temperature were to be increased, this would cause the concentration of the reactants to increase and the products to decrease. The value for K at the higher temperature would become smaller. All right, pressure changes, last type of disturbance we can put to an equilibrium. How can we change pressure? There are 4 ways that you can change the pressure inside of a container. You could add or remove a gaseous reactant or product. Now, granted, that's going to have a similar effect to what's happening with a concentration. So you can basically use those same techniques as well. You can also change the volume of the container. So if you make a container smaller, pressure goes up. So Boyle's law. So going back to gas laws that we talked about. As you make the size of the container smaller, pressure increases, more collisions. If you increase the size of the container, pressure will decrease. So there's going to be fewer collisions on the inside of it. Now, I want to make another note. If you can also increase the pressure of a container by adding an inert gas. If you add an inert gas that does not chemically react with anything else, the pressure inside the container will change. However, the individual partial pressures of the gases that can chemically change, those partial pressures are going to stay constant. And because of that, a increase of pressure due to an inert gas would not cause a shift in equilibrium. So there'd be no change in equilibrium if you were to add an inert gas. And by the way, the inert gas, an inert gas would be one, again, like the noble gases, helium, neon, argon, krypton, xenon, etc. So with that, let's take a look at a couple of examples. What will happen to alleviate the pressure? Now we're going to do one of these together, and then the other two I'm going to have you, or I will do one of them, and then I'll have you do the other two on your own. So what will happen to the equilibrium if the volume is reduced in each reaction? So if the volume is reduced in each of these reactions, once again, that means as volume goes down, pressure goes up because of the inverse relationship between pressure and volume of gases. So if we're looking at this particular reaction here, what we really want to compare is how the pressure can be alleviated if the pressure goes up. So how can we get rid of some of that pressure? Well, the way that we would get rid of some of that pressure is by removing some of the gas or decreasing the amount of gas present. So how would that happen? Well, if I increase pressure on this, well, this is the only gas, that would then drive the reaction that direction. So by increasing the pressure, the only gases that are present are going to shift toward the product side. So that means it will cause the equilibrium to shift toward the products. All right, so that said, what you're trying to do is go to the side of the reaction that has the fewest number of moles of gas. So you're attempting to get to the fewest number of moles of gas if you increase the pressure. If you decrease the pressure, the equilibrium will shift to the higher number of moles of gas. All right, so we've done the first one. Try those on your own, see how it goes. So here's an explanation for all three of them, written out in a more of an essay-style fashion. So for the first reaction, to alleviate the pressure, the equilibrium will shift to the side of the fewest number of moles of gas. So at this point, Q would be less than K and shift to the products. Same thing actually is going to take place in that second reaction. The reason is second reaction, we've got 2 moles of gas on the reactant side, while there's only 1 mole of gas on the product side. So with that, that means the equilibrium to alleviate the pressure will shift this direction. For the last problem, both sides of that equation have 4 moles of gas. Since those are equal, 4 moles on one side, 4 moles on the other, pressure will have no effect on that equilibrium, even though gases are present. So both sides of the reaction have the same number of moles of gas. An increase of pressure will have no effect on that equilibrium system. All right, so here's where you get to flex your muscles a little bit. Here is an entire list of all three. So you'll notice this is an exothermic or an endothermic reaction because the reactants, the energy is on the reactant side of the equation, which means delta H would be positive. Hopefully you remembered that. All right, so the rest of those are going to be adding and removing gases or changing pressure or the like. Give you a moment to do that. All right, so then if you take a look, and one of the things that I did annoyingly not put in the previous slide where it said what happens to the Q when each of those things happen, well, or it could have happened to the value for K, because hopefully you caught that. Taking a look at the values themselves, the first 3 on that page are discussing the idea of concentration. So these, the first 4 are discussing concentration. And hopefully we're able to get how Q was affected and how that's going to compare to the original equilibrium constant. Helium is an inert gas, and so there is no effect of that on the equilibrium position. And then if the container is expanded or compressed, we're talking about pressure, and those are the gases that we discussed. And then last but not least down here are the temperature changes. And once again, the value, oh, hey, I have a mistake there, don't I? One of these should not be larger. One of these 2 should be smaller. Give you a moment to try and figure out which one of those should be which. Typo in the PowerPoint. All right, so if temperature is increased, energy is being added, equilibrium would shift this direction. That means the products would be greater than it was before, than the reactants, which means your K would be a larger value for K. So if temperatures increased, this one will be larger. So then for the last one, that will mean that the last one, this needs to be smaller. So the value for K would be smaller. Let's go through that explanation just to make sure that you are comfortable with it. If we were to decrease the temperature, energy would be removed. By removing the energy, that means the equilibrium will shift toward the reactant side. Reactants will now be larger than it was before, and so your value for K will be a smaller number. So hopefully this quick overview of all of Le Chatelier's principles and the different types of disturbances and their effect on K and Q has been useful for you. Please let me know if you have questions. I will do what I can to help you answer them.